We consider another example in this case where we are considering the flow with no external forces. And as we see, the question is, again the example is taken from our textbook. A spacecraft with a mass of 12,000 kilogram is dropping vertically towards a planet at a constant speed of 800 meters per second. To slow down the spacecraft, a solid fuel rocket at the bottom is fired, and the combustion gases leave the rocket at a constant rate of 80 kilograms per second and at a velocity of 3000 meters per second relative to the spacecraft in the direction of motion of the spacecraft for only a period of 5 seconds. Disregarding the small range change in the mass of the spacecraft, determine the deceleration of spacecraft during this period, that is during those 5 seconds, the change of velocity of spacecraft. If it decelerates, its velocity is going to change, and the thrust exerted on the spacecraft. So these are the three things that we need to calculate, and let us work them out. The force, the net force that is acting on the system have to be equal to the other forces that is we obtain from equation of balancing the momentum. So the thrust force is equal to mass of spacecraft into acceleration of spacecraft. Remember, basically these equations all have started from Newton's second law of motion, and the Newton's second law of motion is F is equal to ma. Now there are various forms in which we write it, in which we calculate it, but basically it originates from there. And so that is equal to beta, the correction factor, flux correction factor, times rate of change of mass into the velocity, and then also at the exit position the same calculation, the force that is acting, where the fluid stream velocity is relative to the inertial reference frame, in this case are identical to the velocity that are relative to the spacecraft. So mass of spacecraft into acceleration of spacecraft can be written as mass into dv by dt. Acceleration is nothing but dv by dt in this case, and this is equal to mass of the gas into the velocity of the gas. So here is a pictorial diagram or picture just trying to depict the spacecraft that is falling downwards with the parameters that have been given in the question. So as we calculate, the acceleration turns out to be 20 meters per second in the negative direction, and it only confirms that the spacecraft is decelerating, not accelerating. If it was accelerating, that would be positive. If it is decelerating, it is negative. And it has a value of 20 meters per second square. Then from this, the value of deceleration, we calculate small change in velocity of the spacecraft will be equal to acceleration into dt. Remember, dv by dt is acceleration. So if we multiply throughout by dt, take it on the right hand side and we make these calculations, and dv turns out to be minus 100 meters per second. And the thrusting force exerted on the spacecraft is from equation 6.2. Again, that is F is equal to ma. So the total forces have to be balanced, and they are equal to F is equal to 0 minus rate of change of mass of gas into velocity of gas. That turns out to be, when we substitute the values, these are the values, and they are equal to 240 kilonewton in the negative direction. So negative direction again indicates that the thrusting force due to the firing of the rocket acts on the spacecraft in the negative x direction. It has to be in the reverse direction. And this force again is equivalent to about 24 tons of mass that is required to its support in the opposite direction of the discharge gases.